Welcome to This Explainer. Okay, I am absolutely thrilled to get into today's topic because we are talking about the ultimate sci-fi dream, anti-gravity. We're going to unpack some wild recent research that proposes a literal quantum loophole, one that could theoretically make gravity repulsive. So, could quantum mechanics actually create anti-gravity? That is the million-dollar question we're answering today. But look, before you rush out and buy ceiling furniture for your upside-down living room, let's ground ourselves for a second. We've got to look closely at the ifs and buts of this fascinating new paper to see how this actually plays out. Right. To understand how repulsive gravity could even be a thing, we have to start by looking at the absolute greatest rivalry in modern physics, general relativity versus quantum mechanics. These are the two fundamental rulebooks that govern our entire universe. And yet, they stubbornly refuse to fit together. Section 1. Two conflicting rulebooks, and why gravity usually attracts. Okay, let's dive into this clash. In Einstein's general relativity, gravity is mediated by a spin-2 field. Basically, that means it acts strictly as an attractive force. The smooth, predictable curvature of space-time. But over in quantum mechanics, particles act like waves that can interfere with each other. Now, both of these systems work absolutely flawlessly on their own, but the second you try to mash them together, the math completely breaks down. The sheer absurdity of it all is summed up perfectly by this quote right here. It's like having two instruction manuals for the universe. One that says, assemble with screws, and the other says, there are no screws. And of course, just as you're literally pulling your hair out, some theoretical physicist walks in and cheerfully asks, hey, have you tried adding 11 dimensions? It is a beautifully frustrating mess that scientists have been banging their heads against for decades. Section 2, the quantum loophole, and testing gravity in the lab. See, for decades, everyone thought that to test quantum gravity, to finally merge these theories, you'd need the insane extreme energies of a black hole or the Big Bang. But recently, physicists realized, wait, we might actually be able to test it right here on Earth using something called an entanglement witness. The idea is, if you can create quantum entanglement between two objects using absolutely nothing but their gravitational interaction with each other, then bingo. Pulling that off in a lab fundamentally proves gravity has quantum properties. But actually running that test relies on a foundational quantum concept, superposition. Basically, you have to put a massive object into two possible locations at the exact same time. The huge roadblock, though, is that the quantum properties of massive objects vanish incredibly fast. They interact with their environment and immediately collapse into a single state. That's exactly why you don't see people walking around in two places at once, and it's also why this crucial experiment hasn't been pulled off yet. Section 3. Making gravity repulsive. This is the core experiment. Now, what's really interesting about this slide is the totally mind-bending proposal for how to test this. Let's enthusiastically walk through these 3 steps to see exactly how gravity creates this repulsive force. Step 1, you take a massive object, the source, and put it in a superposition of 2 places at once. Step 2, you drop a probe particle nearby. Since the source is in 2 places, the probe feels a pull from both locations simultaneously. Normally, if a source is at place A, you're pulled to A. If it's at B, you're pulled to B. But here is the incredible twist for step 3. Because quantum particles act like waves, putting the source in 2 places causes those probability waves to interfere. The probe doesn't just have one momentum anymore, it has several. Through a process called destructive interference, these momentums add up in a completely counterintuitive way that actually pushes the probe away. Boom! Instead of a pull, you get a net repulsion. Now, you're probably thinking what I'm thinking. Doesn't this violate some sort of conservation law? Getting physically pushed away by a purely attractive fundamental force sounds like a literal glitch in the matrix. But the authors assure us, no, the math is totally fine. It checks out completely. To see why it doesn't break physics, just look at this comparison. If you average the results over many, many runs of the experiment, you get exactly what classical physics expects. The probe is attracted to the average location of the source. But in single, isolated runs under superspecific quantum states, you can get this anomalous repulsive effect. It's absolutely crucial to note. This is not some magical, new anti-gravity force. It's an effective force that only happens because of that quantum wave interference we just talked about. But honestly, that's what makes it so cool. If gravity wasn't quantum, this repulsion would be literally impossible. Section 4. The technology gap, and why you can't float to work yet. So, if the math checks out and it doesn't break the universe, why aren't we building this thing today? Well, the brutal reality is the technology gap. Gravity between tiny objects is ridiculously weak, making this physical setup a nightmare to build. The blueprint the authors laid out requires very specific physical materials to even have a prayer of measuring this faint force. They suggest using cesium atoms as the tiny probe particles, but the source mass, that heavy object you have to somehow keep in a fragile superposition, needs to be about 20 micrograms. So, the crucial point is 2 million times. I know 20 micrograms sounds like absolutely nothing, but it is 2 million times larger than the biggest mass our current tech allows us to put in a superposition. That is a staggering gut punch of a technological gulf that we have to cross before we can actually run this test. But hey, it's not all doom and gloom. There is definitely hope for closing that gap. That massive weight requirement could actually come down if we make advancements in these 3 areas. First, increasing decoherence time, basically figuring out how to keep the object in its fragile quantum state longer before it collapses. Second, making our force measurements exponentially more accurate. And third, developing sensors that can resolve way shorter distances in the lab. If we can push the boundaries on those 3 fronts, that 2 million times gap is going to start shrinking fast. Section 5, the final verdict. A skeptical but exciting future. So we're looking at a future that is undeniably exciting, but we definitely still need a healthy dose of skepticism. I actually loved reading a review from another physicist on this paper who said, "I give this a 2 out of 10 on the bullshit meter," basically meaning the theoretical work is rock solid. It's a genuinely credible addition to the literature. The skepticism really just comes from the grueling reality of lab physics. Because even if we close the tech gap, build the device, and actually observe this repulsive wrong-way kick, ruling out that it wasn't just some stray, ordinary force in the lab is going to be exceptionally difficult. And I gotta caution you, the reverse is tricky too. A negative result is totally inconclusive. If we miraculously run this super hard experiment and the probe doesn't get pushed away, well, that wouldn't entirely disprove quantum gravity. It would just mean gravity doesn't have these specific quantum properties in this highly specific setup. The rulebooks might still merge in some way we just haven't thought of yet. Still, physicists are staying hopeful and keeping a great sense of humor about it. Honestly, if this incredibly complex quantum loophole actually works out, we finally have a highly advanced, peer-reviewed scientific excuse for why our hair absolutely refuses to obey gravity when we roll out of bed. So, what does this all mean? Will this quantum loophole finally prove gravity's quantum nature and unlock the universe's secrets of the universe? Or will it just leave us permanently waiting for public transit, totally unable to float our way to work? It's a profound question that really pushes the absolute boundaries of human technology and physics. Keep your eyes on the labs, folks, because the answer might just rewrite the rulebooks forever.